Welcome to Lecture 26, Black Holes. We finally arrived at the most exotic objects in the universe, and after suffering through two lectures now on first special and then general relativity, we finally have a theoretical framework to discuss and begin to understand these objects. So I teased you all semester and told you that when we get to the end, there was some really exciting stuff waiting, and we're finally there. So let's not listen to me anymore. Introduce the subject. Let's just jump in. So as we discussed in the last lecture in the context of general relativity, one of the biggest, the fundamental aspect of general relativity is a complete reimagining of the source of gravity, why gravity exists. And so rather than viewing it in the Newtonian worldview of a long-range sort of magical force, Einstein reimagined gravity as the natural result of a curved spacetime, and that curvature is itself generated by mass. And so, as I mentioned before, the Earth orbits the Sun not because the Earth even really knows the Sun is there per se. All the Earth knows is that its local spacetime is curved, and it moves on a geodesic in that curved spacetime. So but the amount of curvature induced in space-time by mass depends upon the mass and the density of the object. And so, we can look at the Sun, for example, and if you put the Sun in space-time, it creates a distortion, right? If it didn't, we wouldn't be having this conversation because we would not be, at least we wouldn't be like we are now. If we have a white dwarf, it's denser, it's much smaller, and so it curves space-time more in its immediate vicinity. A neutron star is yet denser and smaller, and so it curves it even more. And a black hole is as extreme as you can get, where it's the final stage of a high-mass stellar remnant that is so massive such that even after the core collapses and the supernova occurs, the core remnant that's still there is massive enough that no degeneracy pressure, not even the neutron degeneracy pressure in a neutron star, can balance out gravity. And so the upshot is that if you remember back to the various stages of stellar collapse, first the core, on the main sequence, the core is supported by the radiation pressure that is generated through the nuclear fusion reactions. When that stops, the core collapses and is balanced out by electron degeneracy pressure. When the next stage stops and the helium fusion is exhausted, it collapses again, and with each stage it collapses more and more. Finally, iron is the last thing that can be produced through nuclear fusion, and then the core will collapse yet again before sort of exploding out and generating the supernova. But that remnant that's there again, if even the neutrons formed in the state, as the protons and the electrons are effectively pushed together and converted into neutrons, those neutrons generate an even stronger degeneracy pressure. But if that can't balance out gravity, then no known force can. And so with that, if there's enough mass, then the collapse will continue until the formation of what is known mathematically as a singularity, which is a fancy way of saying a point, a literal point in space with zero physical extent, zero volume, where lots of the physical quantities that we usually use to describe nature go to infinity. So all of the mass will be concentrated at a single point, so the density will be infinite. It turns out that equations don't behave well very often when infinities are involved. But another way of looking at this is that the laws of physics break down at this point. We don't, our theories do not explain how nature acts at a singularity. In fact, in general, singularities in physics don't exist. In general, they're mathematical constructs, but they're predicted by general relativity. General relativity, the equations give rise to a singularity in the case that I've just described, where you have a massive stellar remnant that cannot be counterbalanced by the neutron degeneracy pressure. And so whether there's new physics that emerges that we don't know about yet that actually does stabilize the star at some, at some really, really small size, we don't know. But in any case, the curvature generated by this thing is truly, mind-boggling. And so you can see, the sun made a little dimple. This black hole is like infinite curvature, essentially. So that's kind of the situation that we're looking at now. We've talked about the sun, we've talked about stars, talked about white dwarfs and neutron stars. Now we're going to focus on these, these esoteric things called black holes that give rise to singularities in our space-time. And again, singularity is just a term here that just means place where density, the gravitational force, and a number of other quantities of interest become infinite. So it turns out that we're quite confident in the existence of black holes. But fortunately, there aren't any black holes that are too close to us, and so it's not like we can just go out and touch them and so on. But we've got a lot of computer simulations that kind of show what these things would behave like. And here's a simulated image of what space would look like right next to a black hole, where the blackness is due to the fact that not even light can escape, right? So a black hole is something whose escape velocity is greater than the speed of light. And so if light, on Earth, there's a certain escape velocity from the surface. And so if a rocket ship blasts off at that speed, or if you throw a ball at that speed or greater, then it will escape. But for a black hole, the escape velocity is greater than the speed of light, which means that not even light can escape. And since we know nothing can move faster than light, that means nothing can escape. And so there's this perfectly black region where you just don't see anything because nothing can get out if it were there. And then in the region surrounding that blackness, you see stuff, but it looks kind of weird. It's warped, right? Because the gravitational lensing is extreme, right? This is as large gravitational lensing as you can get when you're moving near a black hole. So there's a movie as well that hopefully that's still up on the web, and so I encourage you to check that out too. So let's now imagine that you're looking at the space-time near the edge of the hole. I put hole in quotes here because we call it a hole because it sucks everything in. Nothing can escape. But there's something we call the event horizon, which is just the point of no return, or the surface of no return. And it's where, if you get inside that event horizon, nothing can escape, not even light. And so for an idealized black hole, it has there's a radius of that event horizon. So if you imagine just an isolated black hole, a point in space, there's a radius, there's a sphere around that, which if you go inside that sphere, you get sucked in and you can't ever escape. If you're outside that sphere, you have a chance of escaping. And the radius of that sphere, or the radius of the event horizon, is known as the Schwarzschild radius. So you can kind of see I don't know how good this perspective is here, but there's plenty of curvature outside the Schwarzschild radius too. So it's not like if you're inside, then you're hosed, but if you're outside, you're fine. If you're getting close to the Schwarzschild radius, close to the event horizon, it's kind of like getting close to a waterfall, right? The closer you get, the stronger the pull gets and the harder it is to get out. So, just keep in mind, if you ever happen to find yourself out in interstellar space, accelerating inexplicably towards apparent nothingness, I would turn and go the other direction as soon as possible. And this event horizon is exactly the point where the escape speed becomes the speed of light. And so on that Schwarzschild radius, or on the event horizon, the escape velocity is the speed of light. Inside it, the escape velocity is larger than the speed of light, which means you're never going to do it. Outside the event horizon, the escape velocity is less than the speed of light, and so if you have, at least in principle, you can escape without violating the laws of physics. Now, whether you actually have a craft, an engine capable of getting you up to those speeds, that's another matter. So again, you don't want to go close to one if you can avoid it. And there's a very simple relationship between the Schwarzschild radius and the mass of the star. If you're interested in where this comes from, it's actually just a few lines of algebra and an application of Newton's law of gravitation. So feel free to reach out and ping me, and I'm happy to show you how that comes about. But the upshot is that the more massive a black hole is, the larger the event horizon is. And so while you can't go inside and like directly measure the mass of the or anything else of a black hole, you can infer the mass of a black hole by looking at its event horizon. So now that I've shown you the simple relationship between the Schwarzschild radius, or which we often refer to as the size of the black hole, and its mass, let's play perform a thought experiment, if you will, and ask, if the sun were to collapse into a black hole, how big would the event horizon be? And while you're thinking about that, or before I shut up and let you think about it in peace, I want to point out too that I just mentioned this term, the size of a black hole, which is a commonly used phrase. But just to clarify, when we refer to the size of a black hole, we really mean the size of the event horizon, the size of the volume enclosed in the event horizon. Because again, the black hole itself, if you will, is a singularity, right? At least according to our best current theories, all of that mass collapses down to a point. So there's no volume in the mass itself, but there is a volume to the event horizon. And so everything inside that is behind a curtain, if you will, and everything outside that you have a chance to see. So if we take our sun then and we collapse it into a black hole, how big would that event horizon be? So it's a straightforward application of the equation on the last slide. You're more than happy to pause me and do that calculation yourself, but I won't make you do that, and so I won't pause here. Before I show you that the sun's current radius is about 700,000 kilometers, and this is the size of the black hole. So if it were to become a black hole, which, just to clarify and remind you, it will not, right? To have a chance of becoming a black hole, you have to be a massive star, more than 8 solar masses. And 8 solar masses won't cut it either, because you will have lost too much mass during the life cycle of the star, most noticeably in the supernova. So you really have to be quite a massive star in order to leave behind a black hole at the end. But you can still ask the question, if you take the sun's mass, how much, and all of it were converted into a black hole, what would the size of that have to be? You do the math and you get about 3 kilometers. Okay, so you go from 700,000 kilometers to 3 kilometers. That's a big reduction, right? It's over a factor of 20,000 reduction. So huge compression required, and again, fortunately, that will not happen to our sun. And there it is in writing. So if you didn't believe me when I said it, you can believe me when I type it. Okay, so let's think a little bit more now that let's imagine we have a black hole here, not from the sun, but from somewhere else, and you went out to observe this black hole. What would happen as you're sort of falling into it? Let's just, you decide, I really want to see what this is like. You watched Interstellar and you got really excited and said, maybe Matthew McConaughey's in there and he'd be really cool to meet. So I'm going to go dive into a black hole. Well, a few things are going to happen. As you move towards this black hole, the gravitational field gets stronger and stronger. But it doesn't get stronger uniformly, because the curvature is so great that even if you're 6 feet tall, say, the gravitational field will start to become noticeably stronger at your feet than it is even at your head. And what that means is that your feet will be accelerated at a greater rate than will your head. And that will stretch you out. This won't feel good. My daughter sometimes asks me, like, how would you feel it? And the short answer is that it would be a really interesting calculation to do to see how long does this stretching process go for? Because if it happens really quickly, then maybe it's over before you know it. If this goes for a while, it's like a natural version of the rack. It would really be unpleasant. And there's a very fancy technical term for this process, and it's known as spaghettification. And it is what it sounds like. Things get spaghettified, they get stretched out, and that's just what happens. So fortunately, I don't perceive any scenario in which this can actually happen to a person, but it does happen to stuff. We observe stuff falling into black holes, and so it's a real thing, and it's got a real fancy term. In addition to that, a person that's watching you as you fall in would see your light being gravitationally redshifted, okay, until you get closer and closer. So if you recall, we talked last time about gravitational redshift, and so it's a natural result of the fact that it takes energy for light to escape the gravitational field. And so again, light can't slow down. The only way that it can give up energy is by redshifting, is by increasing its wavelength, decreasing its frequency. And so the closer you get, the redder you get, until eventually the visible light is shifted out of the visible spectrum even. And moreover, as you hit the event horizon, your clock grinds to a halt. Because you remember that clocks run slower in stronger gravitational fields. Well, you get strong enough and the clock essentially grinds to a halt and doesn't run at all. And so you got slower, 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 and now you appear frozen in time at the event horizon. This sounds kind of cool in the sense that it's very different, but it does not sound cool enough that you actually want to experience it. So, leave this as a theoretical exercise. But since we're all about relativity now, we understand that things look different from different perspectives, physics. Let's reimagine what's happening here from the astronaut's perspective. So, and again, parenthetically, we have to assume that the astronaut's eyeballs are still working after he got ripped apart, but it's theory, so we'll make that assumption. So he would see time in the rest of the universe speeding up, right? He's looking at his clock, and in your own frame of reference, your clocks always run just fine. But he looks out at, if he sees a clock somewhere else in the universe, he sees it running at a faster and faster rate. But interestingly, the event horizon is not a special place for him. It happens to mark the place that he can't turn around from, and so if he's paying attention, he may recognize that. It's kind of like going over a waterfall, or getting close enough to the waterfall that you can't avoid it. But it's not like there's a firewall there. It's not like there's a mark in space or something, or that he would just kind of smoothly move through that event horizon, and then and continue on his way. So to restate what we've said now a couple of different times, once an object passes the event horizon, we have no way to measure it, and there's a simple reason for that, because in order to measure something, we have to be able to get the information out. And so you can imagine if someone were being sucked into a black hole, as we've said, when they pass the event horizon, they don't notice any particular change. So they can still make a measurement if they like. But if they wanted to transmit that measurement to us, they would have to send a signal somehow. Say they send a radio signal. Well, that radio signal travels at the speed of light, but the escape velocity now inside the event horizon is greater than the speed of light. And so there's literally no way to overcome the problem. You can't get information outside of the event horizon. And so so you're kind of stuck. You can't make a measurement inside the event horizon. But the black hole will change a little bit as something passes through into the beyond the event horizon into the black hole. And so it's not completely lost. Not all of the details are lost, but a lot is. And so there are just a few things that you can measure about the black hole. The first is mass, and we can measure the mass by measuring the event horizon, and we've talked about that. a few slides back, I gave an equation relating the Schwarzschild radius to the mass of the black hole. And, qualitatively, a bigger mass means a larger event horizon. Okay. A second quantity that we can measure about a black hole is the spin rate, or is the rate of rotation. So we've talked periodically throughout the set of lectures about the fact that things in astronomy, astronomical objects, tend to rotate. Planets orbit stars, stars rotate, planets themselves rotate, and as things tend to collapse, the rotation rate tends to increase. And we talked about that most recently in the context of neutron stars, which tend to have a very high rate of rotation because they have collapsed to a very small radius. And so the spin rate can be measured in particular by its impact on the space-time around it. Because again, we can't see inside the event horizon, but the black hole, if it's rotating, which most are, it will actually drag space-time around it, kind of like a piece of cloth would be twisted if it's being sort of drug around or grabbed, by something in there. So the spin rate can be measured by looking at the space-time which is outside the event horizon and therefore accessible to us experimentally. And finally, a third quantity that we can actually measure with regard to a black hole is its electrical charge. And in particular, if a black hole happened to swallow a bunch of electrons, it would thereby take on an overall net negative charge, and that would be something that would be measurable because it would have an impact again on the things that are outside the event horizon. And so the upshot here, or the take-home message, is that anything inside the event horizon is inaccessible to us. We can't get anything, we can't get access to the information inside the event horizon. But the mass, the spin rate, and the charge affect the space-time and objects outside of the event horizon, and so we can access those bits of information. So, another way of saying this is that there actually is there is a sense in which we can see black holes. So we can't take a picture of a black hole directly, but we do have some indirect measures or methods of measuring their properties because what's inside the event horizon does have an influence on what's outside the event horizon. And one of those ways is by looking at the X-ray emission from what are known as black hole accretion disks. So accretion disks are what they sound like. So to accrete is to take on or to absorb stuff. And so accretion disks are disks of matter that are being drawn in or sucked into a black hole. And so if we look at the orbits of stars around black holes, that provides us another bit of information. So in particular, again, we can't see the black hole itself, but the black hole has a gravitational influence on the stars that are nearby because of the warping of space-time. And so we can look at those orbits and say, well, if we've got lots of different orbits, these elliptical orbits that are all kind of in the same region of space. And so by looking at all of those things, we can infer through calculation there must be some large mass that we can't see here in sort of the center of all of these things. And so we infer that there's a black hole. Now there's one more thing that we should say that is very often, I should actually say less about it rather than more probably, because there is a lot of misinformation or misunderstanding about this concept, which is known as Hawking radiation. So there is a theoretical method that through which we can see black holes, which was first discovered or recognized by Stephen Hawking. And the details are actually quite complicated, so I will not go into them because the details are beyond the scope of the course, and frankly, they're beyond the scope of the vast majority of researchers. And so, but the important thing is that there actually is a way in which very slowly over time, black holes through quantum mechanical processes can lose energy, which is equivalent to losing mass. And this is often referred to as black hole evaporation. And so while classically, again, according to just Newtonian mechanics, once you form a black hole, it would just stay there forever. Thanks to quantum mechanics, it turns out that that's not true, and over time it will slowly lose mass and evaporate. Now that rate is extremely slow for stellar mass or larger black holes, and so much longer than the age of the universe. But as it turns out, the smaller the black hole is, the lower the mass is, the faster it emits Hawking radiation and the faster it dissipates. And so sometimes you'll hear about concerns about micro black holes, which might be produced, for example, at the Large Hadron Collider or other high energy particle accelerators. It turns out that if such things were ever produced, if by smashing together subatomic particles, we did manage to create micro black holes, those things would be so low mass that through Hawking radiation, they would evaporate faster than they could suck things in. And so you need not worry about destroying the Earth through particle accelerators. But nonetheless, Hawking radiation is something to at least be aware of as a mechanism for black hole dissipation or evaporation over time. And so in principle, I would say we have never actually observed Hawking radiation from a true black hole, but in the very recent past, just in the last few years, condensed matter experiments, which means basically very low temperature, ultra cold atomic gas experiments, have been used to simulate black holes, and in that context, the analog of Hawking radiation actually has been observed. So this is on very solid theoretical grounding, and now has been observed by analogy in the laboratory as well. So again, we're in the land of the esoteric and the very exotic now, but that's what I promised you we would get to eventually, so don't hold it against me. But Hawking radiation is a thing, and it will lead to the evaporation of black holes over very large time scales. So, believe it or not, we've now reached the end of this lecture, so I hope the pain was minimal, and I appreciate you sticking around for it. So, thanks for your attention, and I will look forward to you being back here for the next edition as the light at the end of the tunnel of this set of lectures gets closer. So, until then, have a good night.